And it's my great pleasure to present our today's speaker, Professor Narayanan, and the title is Toeplitz Separators on Quotient Domains. So thank you, Professor Narayanan, for agreeing to have a talk at our seminar, and please go ahead. Thank you.
Thank you very much. So let me take this opportunity to thank the organizers, in particular Alexey, for the invitation to speak here. And of course, happy birthday to Vlad's wife. So let us start. Toeplitz operators. So I'll talk about Toeplitz operators on certain domains. So I'll start with the seminal work of Holmos and Brown on the Hardy space on the disk. Then move on to Workman spaces and then other domains in higher dimensions, and then we'll come to quotient domains. And whatever I'm going to talk about today is joint work with Gargi Ghosh, okay, who was a postdoc here. Okay, so let us start. So I should also warn you that this is comparatively new to me, so I'm still learning various things. So Hardy space, something I'm sure all of you are familiar with. So you look at all holomorphic functions in the unit disk, right? So D will denote the unit disk, and that has a power series expansion, summation a n z to the n, and you have right z in polar coordinates. You have this, and because of the Fourier series, when you take the L2 norm, you get exactly summation an square r to the 2n, and take the supremum over 0 or so less than r less than 1, you're going to get the L2 norm of the Taylor coefficients, right? And this is your Hardy space, so the space of all holomorphic functions in the disk whose boundary values are in L2. And well, you know that it sits inside the L2 of the circle, because L2 of the circle you can think of, so look at the Fourier series, and if you look at Fourier series from 0 to infinity, then you are going to get the Hardy space. So the Hardy space on the disk sits inside the L2 of the circle as a closed subspace. So one has the projection to the Hardy space. So let's go ahead. Since I can't see anybody clear while giving the talk, please feel free to stop and ask questions if there are any. Okay, so we define Toeplitz operators first on the Hardy space. Look at the projection from L2 of T to H2 of D. So H2 of T, remember the Hardy space, it's inside the L2 as a closed subspace. So you have this orthogonal projection. So P will always denote the orthogonal projection from some L2 space to a space which consists of holomorphic functions, okay, like the Hardy space and so on. So once we change to Workman spaces or other domains, P is still going to denote the same projection. Now, the definition of the Toeplitz operator is very simple. You take a L infinity function, a bounded function on the circle, and define TU. So that is going to be the notation for Toeplitz operators. The U is called the symbol. So we are starting with an L infinity function. U is called the symbol. And the definition is simply TUF equal to, so you look at U times F. So U times F is an L2 function. You project it to your Hardy space, right? So that is a very simple operator, and it's possible to, because the Hardy space is the reproducing kernel, Hilbert space, and so on. One can actually write it as a integral operator and so on. Okay, so I'll try to avoid technicalities as much as possible. And it's an easy exercise to see that if TU is 0, then U is 0, because U will be orthogonal to all the exponentials, and so you will have all the Fourier coefficients of U will be 0, and so U is 0. So the map U going to TU, so these are on bounded operators on L2 of T, and this is in L infinity, right? So we are looking at this map, and this is of course 1 1. It's linear and 1 1, right? Because TU is 0, then U is 0, so it's linear and 1 1. Okay, so let's go ahead. So the study of Toeplitz operators was initiated by Brown and Halmos in the 60s in detail. So I'll concentrate only on one result of theirs because that's what we are going to talk about today. There are several results in that paper, which is what essentially laid foundation to the study of Toeplitz operators. Now it is, of course, a sort of a big industry in the sense that there are quite a lot of people looking at it in different directions, including methods from harmonic analysis and so on. Okay, so so as well, it's easy to see that the map we saw earlier, so that u going to t sub u is not a algebra homomorphism. So unlike the multiplication operator, where you are looking at multiplication by u, which is an algebra homomorphism, this is not. And there are easy examples like the unilateral shift and so on, for example. So they Brown and Halmos looked at when TU-TV will be equal to another Toeplitz operator. So we are looking at TU-TV equal to T psi, where psi is another symbol, right? So when is the product of two Toeplitz operator, another Toeplitz operator? Well, the problem had a simple solution in the sense that the conclusion is very easy to understand. This happens if and only if either u bar, so that is a complex conjugate of u, or v is in h infinity of d, so that is simply bounded holomorphic function. So when we define Toeplitz operator, remember that we started with arbitrary L infinity functions, right? Now the conclusion is that conclusion is very strong that that u bar or v should be holomorphic and it should be bounded. Of course, the boundary values are bounded and so on. In which case, you also have that algebra homomorphism property that psi equal to u times v. So whenever TU-TV equal to T psi, one of those things has to happen. Either u bar or v is a bounded holomorphic function d, which means that the Fourier coefficients of u bar, the negative Fourier coefficients of u bar and v, one of them should be 0, right? In which case you also have the product. So an important consequence, immediate consequence is that is the so-called zero product theorem. That means there are no zero devices for Toeplitz operators. If I take two Toeplitz operators and look at the product, TU-TV equal to 0, then so 0 is the Toeplitz operator with symbol 0, right? So it is T sub 0. And so you can apply the previous theorem. It will tell me that first of all, either u bar or v has to be bounded holomorphic function and the product is 0. But then you know that a bounded holomorphic function cannot vanish on a set of positive measure on the boundary of D, right? So on the circle. And so one of them will have to be identically 0. So if TU-TV is equal to 0, then one of the operator is 0. Okay, so this is called the zero product theorem, and I will concentrate essentially on this theorem. As I said, there are several other results of Brown and Halmos in that paper. And from whatever we do, some of those results can also be deduced. So Halmos also asked the general question, what if I take finitely many Toeplitz operators and look at the product of them, and if that is 0, then can you say one of the UJs is 0, right? So one of the operators 0, and this was proved by Lehmann and Vukotic in 2009. So the question was raised maybe in the late 60s or early 70s, and it was proved only in 2009. Okay, and it required quite a lot of new ideas and so on. Okay, so any questions? Okay, good.
Well,
so
you see, usually we have questions at the end, right?
All right, fine, sure. Then I'll go ahead. So now, so our aim is clear. We have an L2 space. We will have space of holomorphic functions sitting inside as a closed subspace. We look at the projection, and whenever you have L infinity functions, you can define these Toeplitz operators, right? And you will see how depending on the space, so we looked at the circle, Hardy space, and so on, the result changes. And in particular, when you look at Bergman spaces, which is what I will be concentrating on, Bergman spaces of bounded domains, the results are quite different from what Brown and Halmos obtained. So we start with the Bergman space, again, one variable. So we look at A2D. So this is the notation for Bergman space we will use. So what is Bergman space? You look at all L2 holomorphic functions, right, on the whole disk, right? So on the open unit disk, this is the two-dimensional Lebesgue measure, right? So dx dy, if you like. And it is known that, so it's an easy exercise to show that A to D is a closed subspace of L to D. So we have this L2 space and we have the holomorphic function sitting inside as a closed subspace. So we will have the orthogonal projection. Okay, so so we define Toeplitz operators on Bergman spaces, just like we define Toeplitz operators on the Hardy space, right? So you look at the projection. So as I said, I'll denote P for these projections. I'm not going to bring in more notation. And you take any function in L infinity of D, the unit disk, then it defines a bounded operator on L2, and then you project it, right? So you project it to the holomorphic subspace, which is a closed subspace of L2D, and you have the Toeplitz operator. And then you can ask the same question. So in the paper by Brown and Halmos, they developed algebraic properties of Toeplitz operators. Okay, when they commute, when the product is a Toeplitz operator, zero product theorem, various results about the spectra, and so on. So you can ask all these questions, and as I mentioned in the beginning, I will be concentrating only on the zero product theorem. Okay, so the zero product theorem for the Bergman space was done by Ahen and Kukovic, and sort of improved, or in a sense refined by Ahen in 2004. So again, you can see that it took several years. The original paper by Brown and Halmos came in the 60s, and this is just in the beginning of this century. So now you start seeing the differences between the results in the Hardy space and the Bergman space. So if U and V are bounded harmonic functions, so this is already a somewhat strong restriction, right? So you're not looking at arbitrary bounded functions. In the result by Brown and Halmos, U and V were just bounded functions. Okay. So here you look at bounded harmonic functions, then you have the zero product theorem. On D such that TU TV equal to 0, then either U or V should be 0. Okay, so you have the zero product theorem. Now, one justification for this assumption that they are bounded harmonic functions is that any function on the circle extends to any bounded function on the circle extends to a bounded harmonic function inside the disk via the Poisson integral, right? So you can sort of think of that. Instead of looking at all L infinity functions, perhaps one should look at some class like this. Now, the zero product problem is open even in the one variable case in its full generality. That means if I take arbitrary L infinity functions, we still don't know about the zero product theorem. Okay, so TU TV equal to 0 implies either U or V is 0 is still not known. Okay, so let us continue. So those were the results for one dimensions. We had the results by Brown and Halmos on the circle, the Hardy space, and then we looked at how the Bergman spaces, and we saw the differences in the results. Okay. All right, so now we go to higher dimensional cases, and you will see again so again, as I said, I will stick to Bergman spaces. There are various ways of improving these results by putting appropriate weights and looking at weighted Bergman spaces or the Hardy spaces or other function spaces and so on. Okay, so I'll just take the case of Bergman space and explain our results. Okay, so let omega be a bounded domain in CD. So the simplest examples or good examples one can keep are the polydisk. So well, this n should be d in fact. So d copies of the unit disk and the unit ball bd in cd. Right. So these two examples you can keep in mind. The Bergman space, as usual, is the closed subspace of holomorphic functions in L2 of omega. And you have the orthogonal projection. So except that now you are in several variables, you have the orthogonal projection from L2 to A2, and you can define the Toeplitz operator, just like what we did in the case of the Hardy space and the Bergman space, right? So you take U to be a L infinity function. The Toeplitz operator has the same definition, right? You take a holomorphic L2 holomorphic function f, multiply by U, project it to holomorphic. Now, one assumption we will always have is the holomorphic polynomials are dense in Bergman space. Okay, this is not automatically true, even though most of the domains we know have this property, and this is not completely characterized. So even in the one-dimensional case, that means we don't have a characterization of um, all domains in all planar domains for which holomorphic polynomials are dense in A2 of omega on the Bergman space. So that is an assumption we will keep, and most of the examples we look at will have this property, like the polydisk and the unit ball and so on. This is automatically true. Okay. So instead of looking at A2 omega, you can also put some weight. Okay, so you look at omega and you look at some appropriate measure and so on, right? So this can be called a weighted Bergman space. The measure can be absolutely continuous and so on. Okay, so let's get on to the results on higher dimensions, and then we will come to quotient domains. So first result again is a zero product theorem for the polydisk. So in 2007, again, somewhat recent, Cho Ku Lee proved that suppose U and V are bounded D-harmonic functions. So remember, we are in the D variable situation. So assumption is that it is a bounded D-harmonic function. So what is a D-harmonic function? So U has D variables Z1, Z2, Zd, and we say it's D-harmonic if it is harmonic in each variable. Okay, so you can say d square by d zj dzj bar, right? So that would be the Laplacian in the jth coordinate, and that is 0. Okay, so if U and V are bounded D-harmonic functions in the polydisk, and there is an extra result, okay, extra condition. So this was not there in the case of Ahern and Kukovic. Once we come to higher dimensions, there are more conditions required. It is continuous on, well, on DD define W, DD union W for some relatively open subset W of the distinguished boundary, right? So the circle, the dth power of the torus is the distinguished boundary of the polydisk, and it has to be continuous on an open subset of T to the D. Okay, if under these conditions we have this zero product theorem, that is if TUTV equal to 0, then either U equal to 0 or V equal to 0. Okay, so for Brown and Halmos, it was just L infinity functions. For Ahern and Kukovic on the Bergman space on the unit disk, you already needed bounded harmonic functions. For polydisk, you needed bounded D-harmonic functions, which is again natural. And you need this extra condition that it extends continuously to some part of the boundary, right? And similar result holds for the unit ball, again by essentially the same people. Either it maybe just Cho and Ku, or yeah, but it's the same people involved. Okay, so let us continue. Now we are going to get into the topic of today's talk. So we saw some results in one dimension and several dimensions. We are going to look at quotient domain. So what do I mean by that? I have some domain in CN or CD, and I quotient it with a group action. Okay. Now the quotient generally is not all that good from geometric point of view. So direct methods sometimes fail in if you look at the proofs for the polydisk or the unit ball and so on. The boundary played an important role there, or the homogeneity of the automorphism group will play a role. Okay, those things fail in quotient domains. So we look at quotient domain. So let me define those things. First, we start with pseudo reflections. Pseudo reflection is a d by d matrix. So just like the reflection, except that you have sigma minus I has rank 1, which means that, and has finite order, which means that you can have a root of unity as eigenvalue, right? In the reflection case, it's just plus or minus 1. So think of, so there is a basis under which the matrix will look like lambda 1, etc., 1, where some lambda to the k equal to identity 1. Okay, so kth root of unity. So any pseudo reflection is going to look like that. So pseudo reflection group G would be a finite group generated by a pseudo reflection, just like a reflection group, right? So examples are finite cyclic groups, symmetric group, dihedral groups. So I would emphasize on symmetric group because that's an easy thing to look at. In particular, you can look at just S2, which is plus or minus 1, and that is much easier to, and you can see essentially everything explicitly in the case of S2. So you take bounded domain omega in CD. So now we are in several variables. If omega is G invariant, so G is a pseudo reflection group, finite. If G acts on omega, that means omega is a J space, then you can form the quotient domain, right? So these are the domains we are interested in. Okay, so let's see if there are examples to talk about. Yeah. So the prominent example is the sorry, symmetrized polydisk. So you look at let me say what is symmetrized bidisk. So that is the easier thing to explain. Symmetrized bidisk. So you look at the bidisk and symmetrize it. So you look at the bidisk, that is D cross D, and you look at the map Z1 Z2 going to Z1 plus Z2 comma Z1 Z2. Okay, so the image is called the symmetrized bidisk, so that is denoted by G2, right? So GD is for the symmetrized polydisk, where these maps, so S1, S2, etc., SD are the jth symmetric. So Sj is the jth symmetric polynomial, right? So here in two variables you have just Z1 plus Z2 and Z1 Z2. So this GD can be realized as omega by G, where omega is the polydisk and G is the symmetric group. Okay, so in particular G2 is D2, the bidisk quotiented with S2. Okay, so that is what one can do. So that is one prominent example which figures in complex analysis, some geometry, operator theory, and so on. Then there are Rudin's domains. Rudin was looking at images of the unit ball under proper holomorphic mappings, and they turned out to be certain quotients like this. And there are certain monomial polyhedrons and so on. Okay, so there are enough examples of this kind. Now, well, before we get into analysis on the quotient domains, we need some results from algebra, and we will. I'll tell you what the analytic versions of these algebraic results are, which is what we will be using. Okay, so this is a well-known theorem in algebra, Chevalier-Shepard Dot Theorem. This says that the invariant ring. So you look at all polynomials in D variable. Okay, so this is polynomial in D variable, and G acts on it, right? Because G acts on CD, so G will act on any function space on CD. And the invariant ring. So what is the invariant ring? So things which are left invariant under the G action. So in the case of the symmetric group, you are looking at symmetric polynomials, right? Is equal to a polynomial ring like this, where theta I are algebraically independent homogeneous polynomials if and only if G is a pseudo reflection group. Okay, so that is one importance of the pseudo reflection group, that the invariant ring or invariant polynomial ring, G invariant polynomials is a polynomial algebra if and only if G is a pseudo reflection. So again, the example is the one which I have been talking about, the symmetric polynomial. So if I look at any symmetric polynomial in D variable, this will have to be polynomials in S1, S2, SD, right? S1, S2, SD are the elementary symmetric polynomials, right? In particular, a symmetric polynomial in two variable is a polynomial in Z1 plus Z2 and Z1, Z2. Right, that's precisely what we are saying, and that is true in general for pseudo reflection groups. Okay, now once you have the pseudo reflection group, you get this theta 1, theta 2, and theta d. Right, these are algebraically independent homogeneous polynomials. So that gives me a map from CD to CD. Right, theta z equal to theta 1 z etc. theta d z is called a basic polynomial map associated to G. So in the case of the symmetric group, it is Z1 plus Z2, comma Z1 Z2. Okay, so what is the importance of this theta? We will see that soon. The quotient domains can be identified using this theta. Okay, and the theta, the map has certain properties. So the thetas come from the Chevalley-Shepard Dot Theorem. So remember that the G invariant ones are polynomials in these D polynomials, right? So I take a G invariant domain in CD where G is a finite pseudo reflection group. It is known that, so these are known results from complex analysis, that first of all theta omega is a domain, and theta from omega to theta omega is proper, and omega by G as a domain is biholomorphic to theta omega. Okay, so since we are interested in the quotient domains, we'll be essentially looking at theta omega. So we study Toeplitz operators on A2 of theta omega. Okay, so if you go back to the example of S2, you see that the map is Z1. In fact, I defined the symmetrized bidisk using that map, right? So I'll be looking at Z1 plus Z2, comma Z1, Z2. These are the basic polynomials map. So this is theta 1 and theta 2 here. The image is my quotient domain. Okay, so theta of omega here is G2, the symmetrized bidisk. Okay, so that is the last one here, right? That omega by G. So D2 by by S2 is identified with the symmetrized bidisk. Okay, and so we'll be studying Toeplitz operator on the quotient domain, which is identified with this biholomorphic copy. Okay, so let's go ahead. Now we need an analytic version of the Chevalley-Shepard Dot Theorem. So let's go back to Chevalley-Shepard Dot Theorem. It says that the G invariant polynomials are polynomials in theta 1, theta 2 up to theta d. Okay, so analytic version would be you replace the polynomials by analytic functions, right? Holomorphic functions. So let's see what that is. So I start with a finite pseudo reflection group and G invariant bounded domain. G hat is the irreducible unitary representations of G. G is finite, right? So irreducible representations of equivalence classes of irreducible representations of G. Now you look at the G action on the polynomials Z1, Z2, Z3. Right, G is a finite group, so it will split according to the representations of G. Right, so you are going to get direct sum rho in G head. So these are representations of G. R rho. What is R rho? R rho is the corresponding isotypic components. Okay, isotypic components. So rho is a representation of G, and you look at polynomials that transform according to rho. Right, that is your corresponding isotypic component. Then, okay, so let's try to explain this in the case of two variables, which is very easy. If I take a polynomial into variable, it decomposes into two parts, right? So remember the group is S2. So if it is invariant under S2 action, it is a symmetric polynomial. Symmetric polynomial. The next sum, well, the other representation of S2 is the sign representation, right? Going the non-trivial element going to -1. So if it transforms according to that, if I flip Z1 and Z2, I should pick up a minus sign, right? That is simply antisymmetric polynomial. But that is easy, right? In the case of Z1, Z2, you simply look at P Z1, Z2. Plus P Z2 Z1, right? So maybe I can write this P Z1 Z2 plus P Z2 Z1. That will symmetrize P, and if I put a minus there, that becomes antisymmetric, right? So that is true in general, except that now you have other representations of G, need not be one-dimensional representations. So one has to define that component appropriately. Now it's easy to see that if I look at polynomials which transform according to a fixed representation, I can multiply it with invariant ones, right? And I will still be in the same space. For example, if I look at symmetric polynomials and I multiply by symmetric polynomials, I will still be there, right? Similarly, if I take anti-symmetric polynomials and I multiply by symmetric polynomials, right? You have to look at invariant ones. I will still be in the space of anti-symmetric polynomials. So that gives me a module action of this invariant polynomials, which is a ring on R row, right? The corresponding isotypic component. And what is known is that this R row, that is the corresponding the row isotypic component, is generated by certain homogeneous polynomials. We'll denote it by L rho J. Okay, and by degree rho square, that many polynomials. Okay, so again, the easy example is the symmetric polynomials and anti-symmetric polynomials. This is generated by the constant function 1, and this is generated by Z1 minus Z2. Right, symmetric polynomials are generated by 1, right? 1 times all G invariant polynomials, that is all symmetric polynomials. And similarly, anti-symmetric polynomials are, because they vanish on Z1 minus Z2, it will be divisible by Z1 minus Z2. And when you divide by Z1 minus Z2, you're going to get a symmetric polynomial. So that is all is there. Okay, and that is true in general. So let me continue with analytic version of the Chevalier-Shepherd Dot Theorem. So analytic, so remember that from the Chevalier-Shepherd Dot Theorem and representation theory, we were able to write the polynomial ring as a direct sum, right? So we called it R rho, where rho in G hat, right? So these 4 young mathematicians from India, as Biswas, Datta, Gargi Ghosh. So Gargi Ghosh is the co-author of whatever I'm talking about, and Subrata Sham Roy, which appeared very recently, just last year, proved this for all holomorphic functions. Okay, so every holomorphic. So you look at holomorphic functions on omega. Okay, and look at the G action there. Right, just like polynomials, you can look at that, and then it will decompose according to the representation of G. But then what they have proved is whatever you saw in the case of polynomials, it continues to hold for holomorphic functions as well. Okay, so for every holomorphic function f on omega, there exist unique G invariant holomorphic functions f rho j such that f can be written expanded in terms of L rho j. What was L rho j? Remember, so let me go back one page just to remind you what L rho j is. In the case of polynomials, the isotypic components were generated by these L rho j's. So these were the basis for the isotypic components, and you know the module is generated by these homogeneous polynomials. Same basis works for holomorphic function. Okay. Now that was an important result, and their proof is completely different. So it is I mean, it is tempting to look at the polynomial case and then see how it works for holomorphic functions and look at convergence issues, right? But that is not how this is done. That doesn't seem to work all that easily. This is a completely different proof, okay? But it is quite a strong result, I would say. Any holomorphic function can be expanded. So in the case of S2 and G2 again, if I have a holomorphic function, here again this is trivial because just like what you did for polynomials, you can symmetrize it first. Z2, Z1, so you flip it, right? Plus the antisymmetric one. Now the antisymmetric one, Z2 Z minus this divided by 2, right? So the antisymmetric one vanishes on the variety Z1 minus Z2 equal to 0, right? On Z1 equal to Z2. So since it's a holomorphic function and Z1 minus Z2 is irreducible, it will be divisible by Z1 minus Z2. So this is going to look like Z1 minus Z2. So remember the constant function 1 and Z1 minus Z2 were the generators, right? And the same generators work times symmetric holomorphic function, right? So that is what the proof for D2 quotiented with S2 is. Okay, so that is easy, but this is true in general for pseudo reflection groups. Okay, so let us continue. Yeah, I might finish quite earlier than time, but let's see. So now we go to some more representation theory, sign representation. So if you have a pseudo reflection group, there is a sign representation. So that is sign G equal to determinant of G inverse, and you can see that as a character. So it's a one-dimensional representation. Now go back to the Chevalley-Shepard Dot theorem. And the corresponding decomposition with respect to representation. So each representation came with a set of generators, right? So R rho was generated by L rho J, right? And J was going from 1 to degree rho square. Degree rho meaning the dimension of the representation. So when the dimension is 1, there is only one generator, right? So remember S2 case again. In the symmetric polynomial case, it was just the constant function 1. In the case of antisymmetric functions, it was Z1 minus Z2, right? So these are one-dimensional representations and you have one generator. So here, since sign representation is a one-dimensional representation, you have a single generator, so which we call by L sin Z, and that turns out to be an important object called the complex Jacobian, right? So you look at the theta map. So remember the theta map which came from the Chevalley-Shepard Dot theorem. Theta was theta 1, theta 2, etc., theta d, and these were the G invariant generators for the G invariant polynomials, right? So and that gives me a map, and so there is a Jacobian, a complex Jacobian, and you look at the determinant. Okay, so this is going to play a crucial role. So now let's look at the Bergman space. So A2, remember, is the Bergman space. G acts on A2 omega, right? Because G acts on omega, so G will act on A2 omega. Okay. And A2 omega is a Hilbert space, so it decomposes into, in fact, it's an orthogonal direct sum of spaces where A2 rho, the subscript rho means just like R rho. It is the collection of holomorphic functions in A2 omega, which transform according to the representation rho, right? So A2 omega decomposes into this orthogonal pieces. There are only finitely many, right? So you have finitely many pieces like this. And result by Gargi Ghosh says that the map gamma from A2 of theta omega. So remember, we are interested in Bergman spaces over quotient domains, and we want to study Toeplitz operators there. So now we are trying to realize it as some subspace inside the Bergman space of the original domain. So A2 sign is one piece here, right? So A2 omega. So A2 omega well, there is something called the trivial representation. So these are the invariant ones. There is some other representation, and there is one for the sign representation, right? So the result by Gargi says that the map gamma, which is from A to theta omega, so that is the Bergman space, downstairs meaning the quotient space, to A2 of sine omega, which is one piece of the Bergman space of the original domain omega, given by gamma fz equal to 1 by root of mod g, that is a constant, forget that, f of theta z times j theta. Okay, so f of theta z would make it into a function on omega, right? So I have omega, I have theta of omega here, and this is the map theta, right? I'm looking at functions here, holomorphic functions here. I pull it back by composing it with theta. I'll get a function on omega, and I multiply with the complex Jacobian. Then I'm going to get something in A2 sine. Okay, that is what it says. And the map is unitary. So this helps us to identify the Bergman space on the quotient space with some piece of the Bergman space in the original domain. Okay, so in the again example is, you take the polydisk, then it is easy to compute that the Jacobian is simply the product of zi minus zj. So you take any function in the symmetrized polydisk, multiply by j theta, and pull back the function to omega, you will get something which transforms according to the sign representation, right? In the simplest case of symmetrized bidisk, you will be looking at f times z1 minus z2. Right, see, f pulls back to omega as a symmetric function, right? Because if you are already on the symmetrized bidisk, the functions there when pulled back to the bidisk will be symmetric, and I'm multiplying by z1 minus z2, so that becomes antisymmetric. So it goes to the sign representation. Okay, so I hope this is clear because this is important for us. Now we are in a position to state the zero product theorem on quotient domains. So we start with a quotient domain theta omega. Let's take u and v be bounded functions. Then, so remember, I have omega, I have theta omega downstairs. This is theta. So any function here, so let's take u. U is a function from here to, let's say, complex plane. I can pull it back. So I'll get u tilde, which is u composed with theta. Okay, it's the same function, except that now you go to the original domain omega as a symmetric function or as a G invariant function. Okay, because theta omega is omega by G, right? So any function on omega by G pulled back to omega becomes a G invariant function. That is all I'm saying. So the tildes will always stand for things which are upstairs, that is for the original domain. So you take two bounded functions on theta omega, which is downstairs, the quotient domain. You pull it back, you get G invariant functions on the original domain omega. Now, since they are all bounded functions, you can define Toeplitz operators on both the spaces, right? So you have TU-TV to be Toeplitz operators on the quotient domain, Bergman space over the quotient domain. You pull back U and V, you get Toeplitz operators on A2 of omega, the original Bergman space, okay, or Bergman space over the original domain. Now our main theorem is this, which is very simple. It's a zero product theorem. TU-TV equal to 0 on A2 of theta omega. That means we are looking at the zero product on the Bergman space in the quotient domain. If and only if you pull back them to the original domain and you have zero product there. TU-TV equal to 0 on A2 of theta omega. If and only if Tu tilde TV tilde equal to 0 on A2 of omega, right? So you pull back them. So consequently, so because of this result, Whenever you have a zero product theorem on the original domain A2 omega, that will immediately imply a zero product theorem on A2 of theta omega, right? Because tu tilde tv tilde equal to 0 implies one of them to be 0, and then of course that holds on the quotient domain. So in particular, zero product theorem on the polydisk. So remember the results by Cho, Ku, and Lee on polydisk or the unit ball and so on. You can look at the symmetrized polydisk or Rudin's domain because they are all quotient domains, and in the original domains there are zero product theorem by these people, and they all descend to zero product theorem on the Workman space over the quotient domain. So in particular, the zero product theorem on polydisk. So one can actually write down. So as I said, I wanted to avoid technicalities. So it's possible to, for example, the result on the symmetrized polydisk, one can write it as a slightly more explicit result. Okay, so instead of simply saying this, you can define things on the symmetrized polydisk and say that certain, I mean, instead of saying d-harmonic function and you push it down to the quotient domain, you can sort of explicitly say what happens on the polydisk, symmetrized disk itself. Okay, so I'll finish with the sketch of the proof. Now it should be more or less clear to you. So you start with A2 of omega, that is our original Workman space over omega. Decompose it with respect to the representations of G, right? This is the representation, this is the decomposition with respect to G hat, right? So there is one which is trivial, there is one which is sign, right? These two are explicit representations. Trivial would mean G invariant functions, right? So these are G invariant. Sign representation was defined, so this was the determinant G inverse essentially. And you look at that part by Gargi-Ghosh's result that can be unitarily identified with A2 theta omega, which is our object of interest, via the map gamma, right? You take something in A2 of theta omega and you multiply it with the complex Jacobian, right? That is the map, right? That is gamma inverse, if you like, or gamma. Now, well, now you do the obvious thing. So if tu tv equal to 0 on A2 theta omega, so that is the smaller domain. So let me A2 of theta of omega. I have A2 of omega, that is A2 trivial, direct sum several things, direct sum A2 sign, right? So these two are identified. So TUTV equal to 0 downstairs implies TUTV equal to well, TU tilde TV tilde equal to 0 on A2. So when I say tilde, I have gone to the original domain. Okay, so these are happening on the original domain. So TU tilde TV tilde equal to 0 only on a smaller piece, right? On A2 of sign domain. But remember, U tilde and V tilde are G invariant. So now use the analytic Chevalier-Shepard Dot Theorem. You start with something here, expand it in terms of those generators, and use the fact that U tilde and V tilde, right? U and V pulled back to omega are G invariant. So one goes to all the other pieces. So there are several pieces here, right? So all of them, the product U tilde TV tilde will be 0, and so it will be 0 on the whole space A to omega, right? So whenever you have a zero product theorem on the whole space A to omega, you have a zero product theorem on the quotient space. So this is the final result. And well, there are various improvements one can do, which I didn't talk about. One is you can look at a measure on omega or a weight on omega, which is G invariant, and the same proof will go through with appropriate modification. And also, from whatever we have done, we are getting a relationship between Toeplitz operators on the quotient domain with the restriction of the Toeplitz operator to a certain subspace of the original domain, right? And from that we can go to the whole domain using various invariance properties. And this will also give us when they commute and things like that. So some of the other results which Brown and Halmos proved on the Hardy space, or people like Cho, Cooley, and so on, proved in the case of polydisk or the unit ball, can be proved in the quotient domains as well. Okay, so that is all I want to say. Thank you for your attention.
Well, thank you very much for very nice presentation, and we have time for questions. So please, questions. Maybe meanwhile I have one general question. Can omega be a half plane?
You are asking how to view half plane as a quotient domain?
No, I mean, if you know results for disk, can you go from disk to half plane by your technique, or it's not possible?
No. So, okay, first of all, when you change the domain, things change. So half plane, first of all, will be an unbounded domain.
Yeah.
So unless you put some weight, polynomials are not in L2.
No.
Or, I mean, why half plane? You can look at the Fock space, right? All entire functions which are square integrable with respect to an exponential weight. Such spaces. Yeah, our results won't imply any of that.
But maybe question is like that. Can you develop the same technique for half plane? Or for unbounded domain?
I see. Okay. Yeah, I don't have an answer.
Yeah, maybe it's a question
because
for study.
One has to see. Well, so the general principle is that if you have a nice group acting on some space, this method of using the representation theory and coming down to the quotient space, that is general. That works in various places. But what we are doing is we are deducing the result for the quotient domain from the results on the original domain. But yeah, in general, it may be possible to do something similar for other domains as well, even unbounded domains.
I see.
Yeah. But I don't have a precise answer now.
I see. Well, and maybe one more question. You see, I was interested in the question where the product of two Toeplitz separators is also a Toeplitz separator. Of course, for some particular cases of symbols, and I had some partial answers. But do you consider such type of problem?
Well, so our technique will work in that case as well. Again, if there are results in the original domain, then there are results in the quotient domain from our results.
Okay, perfect. So I'll send you some papers of mine that we can discuss later.
Yes,
Okay. Okay. Good.
Yeah, thank
you. Perfect. Thank you. So maybe more questions. Sometimes I don't see hands because so many people here.
Yes. Yeah.
Well, but we had a very nice discussion anyway, and well, if no more questions, let's thank speaker for a very nice presentation.
Thank you very much.
Thank you.